So far our progress is as follows. We have defined Lebesgue outer measure and we have collected a few nice properties of Lebesgue outer measure, such as Lebesgue outer measure is monotonic, it is translation invariant. For a countable set, Lebesgue outer measure is 0 and Lebesgue outer measure is countably subadditive. These are some nice property that we observed. There may be much more. However, these nice properties that we have collected should not tempt you to believe that Lebesgue outer measure is a perfect way of measuring subsets of R. One should not think that Lebesgue outer measure is a perfect way of assigning measures to subsets of R that is consistent with length of an interval. For instance, if it were a perfect way of measuring, then we should expect that measure of disjoint union of two sets will be equal to sum of the measures of the individual. Measure of a whole is equal to sum of its parts. But this does not happen for a Lebesgue measure. And that is exactly the content of the theorem, what we want to prove next. And theorem reads as follows. There exists sets capital A1 and A2 in R. A1 and A2 are disjoint. We can write here itself. There exists disjoint sets A1 and A2 in R such that Lebesgue countermeasure of the union of those two sets does not coincide with Lebesgue countermeasure of A1 plus Lebesgue countermeasure of A2. And once we prove this theorem, we are convinced that Lebesgue countermeasure is not a perfect way of measuring sets. So far, so good. And I think this was the last theorem that we stated in our previous lecture.
Yes, sir.
Am I right?
Yes, sir.
Yes, sir.
So let us proceed with the proof. And the approach to this theorem is very clever, as follows. In order to prove this theorem, let us go by contradiction. Suppose for a moment that this does not happen, means there does not exist a pair of disjoint set satisfying this condition. Suppose for a moment that what does it mean? This does not happen means M star of A1 union A2 is equal to M star of A1 plus M star of A2 for all A1 A2 subsets of R, A1 A2 disjoint. Is true for any two disjoint pair of subsets of R. That's what we mean by the theorem doesn't hold. Okay. We will be referring to this quite often. So let us call this as star. To put in simple language, star says that M star is additive. That is, M star is additive. Once star 1 holds, let me put it as star 1. Once star 1 holds, you can apply induction and you can prove it for finite number of sets. Okay. Then we have M star of union AI, I is equal to 1 to n, is equal to summation I is equal to 1 to n M star of AI for pairwise disjoint sets A1, A2, and so on AN in R. Once we have star 1, we have star 2 as well. Please keep in mind that we already proved M star is countably subadditive. Now, as we did in one problem in the tutorial sheet, we are going to prove that once we have countable subadditivity and additivity, we will get countable additivity with the help of monotonicity. We have proved that in one problem, but let us repeat this for the sake of completion. Now consider, so we had it for a pair, we pushed it further to finite number of pairwise disjoint sets. Now I am going to consider denumerable number of pairwise disjoint sets. Now consider a denumerable, countably infinite, disjoint family AI. I belong to N. AI intersection AJ equal to null set for I not equal to J in R, family of subsets of R. Okay. Then the following facts are trivial. With the help of properties of M star we developed so far. Summation I is equal to 1 to n M star of AI for an n belonging to n infinite. This is equal to M star of union I is equal to 1 to n AI. This is by star 2. Okay. And this is less than or equal to M star of union I is equal to 1 to infinity AI. Do you agree?
Yes, sir.
Yes, sir.
How does it follow?
Monotonicity.
Monotonicity of M star. A subset of B implies M star of A less than or equal to M star of B. And that is less than or equal to summation I is equal to 1 to infinity M star of AI irrespective of whether AIs are disjoint or not. And this follows from countable subadditivity of M star, which we have already proved. Thus, what we observed is the following. Thus, for any fixed natural number n, summation I is equal to 1 to n M star of AI is less than or equal to summation M star of, I am just consolidating our observation. This is less than or equal to M star of union I is equal to 1 to infinity AI, which is less than or equal to summation I is equal to 1 to infinity M star of AI. This is true for any n in n. Now you let n tending to infinity, taking limit as n tending to infinity. When I say limit, I am allowing the limit value to be infinity as well. We have summation I is equal to 1 to infinity M star of AI is less than or equal to M star of union I is equal to 1 to infinity AI is less than or equal to summation I is equal to 1 to infinity M star of AI. And that provides you, that is, summation I is equal to 1 to infinity M star of AI is equal to M star of union I is equal to 1 to infinity AI. So let us recall our progress so far towards the proof. We want to prove that there exists a pair of sets A1 and A2 such that mu star of A1 union A2 is not equal to mu star of A1 plus mu star of A2. For the time being, we suppose the contradiction. Suppose there does not exist a pair satisfying that condition. That will give you that M star is additive on two sets, two disjoint sets. And that, with the help of monotonicity, countable subadditivity, etc., provided you that then M star forces to be countably additive. Is that okay? So far, so good?
Yes.
And this I will put as star 3. So once I have star 1, then automatically I can push it up to star 3 with the help of properties of M star. But what I want to get is a contradiction. Star 1 does not happen. That's what I want to get to prove the theorem. To show that star 1 does not happen, I will prove that star 3 does not happen for certain denumerable collection AI. So now I am going to construct a denumerable collection AI for which star 3 does not happen. That will in turn give me star 1 does not happen. Is that clear?
Yes.
Yeah. So let us, now we will show that star 3 does not happen for a certain denumerable disjoint family AI. I is equal to 1 to infinity of subsets of R. So once I can prove that there exists a disjoint family violating star 3, then I can convince myself that star 1 does not hold, and that will give me a proof of the stated theorem. Okay. Now the stated theorem I will call as T1. So proving T1 boils down to finding a denumerable disjoint family of subsets for which star 3 is violated. Now, how do you do that? For that, I have the following theorem, which I will call T2. So to prove theorem T1, I will prove theorem T2, which reads as follows. There exists a subset E of R and such that there exists a subset E of R such that if I let En is equal to E plus Rn, translation by an amount Rn, where Rn is rational number for n belong to n, with set Rn n belong to n being enumeration of rational numbers in -1, 1, then so I am going to construct a set E. From E, I am going to get a family of subsets En by translating E, and this En will satisfy the requirement that we want. Then the disjoint family, Ens will be disjoint, collection En, n belong to n, satisfy 1 less than or equal to m star of union En less than or equal to 3. N is equal to 1 to infinity. In particular, m star of union n is equal to 1 to infinity En is not equal to summation n is equal to 1 to infinity m star of En. That particular part is what we are interested in. Okay. Again, let me repeat. We wanted to prove theorem T1. We observe that proving theorem T1 is same, or is to prove a theorem T1, it is enough to prove star 3 does not hold. And in order to prove star 3 does not hold, I am making a statement which I call theorem T2. And theorem T2 tells you that you can construct a subset E and its translations E plus Rn such that these E plus Rn's are disjoint and E plus Rn will violate star 3. Will violate star 3. Is that clear?
Yes, sir.
See the last part of theorem T2. You have a countable disjoint family of subsets such that m star of union is not equal to summation m star. That means star 3 is not satisfied. That means star 1 is not satisfied. That means theorem T1 is true. So we are proving theorem T1 via theorem T2. Okay. So now the question boils down to how do we prove theorem T2? How do we construct such a set? It is an existential statement. We have to prove that there exists a set E with these set properties. Okay. And the proof will be based on axiom of choice. Okay. We prove theorem T2 by invoking the axiom of choice. You might have used the axiom of choice in several places, but let me quickly recall what it is and then go back to the proof of theorem T2. Does it sound good?
Yes, sir.
Yes, sir.
Okay, so let us quickly recall what is axiom of choice. Background. In fact, the axiom of choice is, at least in appearance, is a trivial statement. Okay, it's a trivial statement. So let us understand axiom of choice as follows. For instance, you assume that you are provided with a box, let us say, filled with some objects, say balls. You have a box, okay, in which you have several balls. I am asking you to get one ball from that box. Can you do that? I'm asking you to go and get me one ball. So you will go and arbitrarily pick one. No, you can pick one from that box. Now, instead of one box, suppose you have n boxes filled with balls. And I am asking you to go and pick one ball from each box. Get me one ball from each box. Can you do that?
Yes, sir.
Yes, sir.
Go to the
Yes.
first box, get one. Then go to the second box, get one. Then go to the third box. I stress the word then. Then go to the third box, get one, and so on. So I can get a ball from each box. So what I am doing basically is I am getting a representative from each box. Okay. Or maybe instead of boxes, you can think like you have n states of India. And I want to get a parliament consisting of one representative from each state. I want to form a collection with one representative from each state. Can I do that? Obviously, go and pick one from each state arbitrarily. Okay, so like that, I can form a set consisting of, or a group consisting of representative of each state. Now I want to change these situations in a mathematical language. So you are dealing with collections. Okay. So basically you are dealing with sets. And you are doing some selection operation on the sets. The operation is selection. And what is basically operation on sets? Those are functions. So if you want to change this situation into mathematical language, what we have basically is sets and functions. Okay, so let me write. Let A1, A2, and so on, AN are non-empty sets, maybe boxes, maybe different states in India or whatever it is. Non-empty sets. I want to find a representative from each of these sets. That means consider a function f from I, where I is 1, 2, 3, etc. up to n, to union AI, I is equal to 1 to n, such that what f does, f of I is in AI. I am getting one member from one state and I want to form a parliament. I want to take a representative from each state. And this function is called choice function. And what it does is choosing one element from each set. The so-called choice function. So the question, can we get a set consisting of one representative from each of these sets, boils down to, can we have a choice function? Is that clear?
Yes, sir.
Yes,
Yes, sir.
Getting a set consisting of one representative from each of these non-empty sets is equivalent to getting whether there exists a choice function. Isn't it? Do you agree?
Yes, sir.
Now let me put in another words. Now, you know the Cartesian product of A1, A2, A3 and so on. Here you have only finite number of sets. Okay. Recall A1 cross A2 cross etc. cross AN is equal to, by definition it is, collection of all pairs A1, A2, A3 etc. AN such that AI is in AI. I from 1, 2, 3, etc. First coordinate comes from A1, second coordinate comes from A2, and so on. Nth coordinate comes from the nth set, capital AN. This is the Cartesian product of finite number of sets. Now, suppose you have a choice function, f from I to union AI. Then you can have f of 1, f of 2, and so on, f of n. Okay, consider a choice function. Consider a choice function f from I to union a I varying from 1 to n. Once you have a choice function, I can talk about f of 1, f of 2, so on, f of n. I can put it as a n tuple, and do you see that this will be an element in A1 cross A2 cross etc. AN?
Yes, sir, it is.
Because by very definition, choice function is such that f of I is in AI. Therefore, once you have a choice function, you have an element in the Cartesian product. Conversely, suppose I am giving you an element in the Cartesian product. Conversely, suppose B1, B2, and so on, Bn is in A1 cross A2 cross etc. cross AN. Okay. Question is, can we get a choice function?
Yes, sir.
What do you see? Can you define a G from
Yes, sir.
I to union AI such that G of I is in AI? Can you define?
Yes, sir, we can.
How do I define? Define G of I as
Equals to BI.
BI. Okay. Conversely, suppose this is there, then we can find a choice function G from I to union I is equal to 1 to n by defining G of I is equal to Bn. So given a choice function, you have an element in the Cartesian product, and given a element in the Cartesian product, you can have a choice function. That means somehow the Cartesian product can be identified with collection of all choice function. Do you agree?
Yes.
Every element in the Cartesian product give rise to a choice function, and every choice function give rise to a element in the Cartesian product. So there is a correspondence between choice functions and elements in the Cartesian product. Thus, the Cartesian product A1 cross A2 cross etc. cross AN can be identified with the collection of all, the set of all choice functions. So let me give a notation for it. Collection of all F from I to union AI. I varies from 1 to n. And what is I? I is 1, 2, 3, etc. up to n. Such that F of a fixed I is in the set AI. This is choice function. You collect all choice function and call it as, let us say, script F from I to union AI. Collection of all functions from I to union AI, 1 to n. And to indicate choice function, I will put as FC. This is how I define. Okay. So A1 cross A2 cross etc. cross AN can be somehow identified with FC. Okay. A1 cross A2 cross etc. cross AN is identified with the collection FC. I union AI. Okay. I is equal to 1 to n. So existence of choice function is same as existence of an element in the Cartesian product. Do you agree?
Yes, sir.
Yes, sir.
So all these things are under the simplest case when you have finite number of sets. Okay, choosing a representative from each set is same as constructing a choice function. Constructing a choice function is same as getting an element in the Cartesian product. Okay. Now let us push it further. Why only finite case? Okay. Next, let us consider an indexed family of A alpha element of some set gamma of non-empty sets. Where this gamma can be finite, like we considered the case previously, 1, 2, 3, etc. up to n. It can be denumerably infinite, 1, 2, 3, etc. Or it may be uncountable. Okay, now there is no restriction on the size of this gamma. It can be finite, it can be denumerable, or it can be uncountable. Something like you have an interval 0, 1, and for each time in 0, 1, you have a set 80. For each t, each time, you have a set 80. Okay, so you have a uncountable collection of sets, non-empty sets. Okay, then the choice function is a function f from where the indexing set to union of those sets, union A alpha in.
Index.
We don't have any difficulty to define union. Please bear in mind. We don't have any difficulty to define union, be it finite number of set, be it countable number of set, or be it uncountable number of set. We don't have any issue to define union. Okay, such that f at some alpha is in A alpha for all alpha in this indexing set gamma. Okay, this is choice function. And how do you define the Cartesian product? And the Cartesian product is defined as Cartesian product alpha in gamma A alpha is defined as. This is why the identification become important. Remember, the Cartesian product we have identified as collection of all choice function. Yes or no?
Yes, sir.
Yes, sir.
So in this case, that is the way in which we are going to define Cartesian product. The Cartesian product is defined as F C gamma union A alpha in this. What is this collection? That is the collection of the set of all choice functions. Choice functions. Okay. So this is the definition of Cartesian product. Choice function. That is Cartesian product A alpha in gamma is equal to set of all functions identified with set of all functions from gamma to union A alpha in gamma, capital gamma, such that f of alpha is in A alpha. So this is the definition of Cartesian product. See now the importance of identifying the Cartesian product as the collection of choice function. Only because of this identification, we could push the definition of Cartesian product to arbitrary sets. For an arbitrary family of sets, the Cartesian product can be defined only via choice function. You cannot take the something like tuple x1, x2, x3, and so on. That doesn't make sense. See, Cartesian product originally we defined as the tuple x1, x2, x3, etc. up to xn. If you have denumerably infinite, you can call it as x1, x2, x3, and so on. But if the family is uncountable, x1, x2, x3, so on doesn't make sense. Are you with me?
Yes, sir.
Yes.
So
Yes,
this
sir.
is the way, this is the only way in which you can define Cartesian product in case you have uncountable number of sets involved. Okay, so this is the definition. Cartesian product is defined as collection of odd choice function. Okay, so that's not what we wanted to say. This is just an identification. So this is the definition of Cartesian product. Okay, I don't know whether you have seen this symbol. This symbol with the two dots and an equal to means equal to by definition. Okay, it is the definition.
Defined as.
Yeah, it is defined as. These two are equal by definition. That is the definition. That's it. Okay. Now the question is the following. The question is the following. Suppose we have an indexed family. Indexed family of non-empty sets. Let us call A alpha, where alpha varies over some sets which can be finite or countable or uncountable. Okay. Question is, does there exist a choice function F from indexing set to union A alpha in such that choice function means F of alpha is in A alpha. In other words, existence of choice function means existence of an element in the Cartesian product. In other words, whether the Cartesian product is non-empty. Cartesian product is non-empty. What is the Cartesian product? Simple, we gave product X alpha element. So this is the question that one faces immediately after defining. Okay, given an indexed family, does there always exist a choice function? And it is same as asking whether the Cartesian product has some element in it, whether the Cartesian product is non-empty. The question at first sight may appear like it is ridiculous, it is trivial, because you can say like, go and pick one element each time. You pick an element from A, you pick an element from A beta, you pick an element from A gamma, and so on. But the issue is, what do you mean by go and pick one each time? If it have only finite number, I can pick one from A1, secondly from A2, thirdly from A3, and so on. If you have countable number, then also it makes sense. But remember here, the family is an arbitrary indexed family. So going and picking one at each time doesn't make sense. Each means what? Are you getting me?
Yes, sir.
So that is why this question is not trivial as first we think. It is not trivial. And the answer is given by axiom of choice. Answer to this question is yes, and that is axiom of choice. Remember, it is just an axiom. It is a statement which we believe to be true. It is self-evidently true. Because of our intuition with certain practical cases, we feel that the statement is true and we take it as an axiom. And now what is the axiom? Let me state it properly. Axiom of choice. Given a non-empty collection of non-empty sets, of non-empty set the Cartesian product is non-empty. Very funny statement. There are lot of non-emptiness there. Given a non-empty collection of non-empty sets, the Cartesian product is non-empty. What does it mean? What is given to you? You are given with collection A alpha, alpha belonging to gamma. This gamma is non-empty. That is what you mean by non-empty collection. This gamma is non-empty. And for each alpha in gamma, you have a set A alpha. Those A alphas are non-empty. That is the second one. Non-empty collection of non-empty set is given to you. Now, we can always assert that there exist elements in Cartesian product. That is same as saying
Existence of choice function.
choice function. There exists a choice function. That is, let me write in that language also. That is, given an indexed family of non-empty sets, A alpha, alpha in lambda, but this indexing set is not empty, non-empty collection of non-empty sets, then there exists a choice function. F from gamma to union alpha in gamma A alpha. There exists a choice function, or in other words, product A alpha, alpha in gamma, that is Cartesian product, is non-empty. So these are all various ways of saying. So given a collection of sets, you can always form a set chosen by, formed by taking a representative from each sets. Given a collection of sets, you can always form a new set by taking one representative from each set. Given a collection of states, you can always form a parliament by picking one representative from each state. Okay? This each state, etc., you will feel it trivial when you have finite or countable. When things are non-trivial when you have an uncountable family. Okay, so this is an axiom. This is believed to be a self-evident truth. So there is no question. You cannot question it. You can believe it. Okay. Is that okay?
Yes, sir.
Yes, sir.
So axiom of choice simply says that if you have collection of sets which are non-empty, you can form a new set by picking representative from each set. Okay. You can form a new set by picking representative from each set, or you can form a choice function. Okay. This is an axiom. And there are some few lemma that is based on this axiom. One is Sohn's lemma. Have you heard about it?
Yes, sir. John's lemma.
Once you believe axiom of choice, you can prove a lemma, that is Sohn's lemma. What is that? What is Sohn's lemma? Can somebody recall?
Every non-empty subset of set of natural number has a least element.
That is not Sohn's lemma. Sorry.
Every bounded chain is maximal element.
In a partially ordered set, every chain, if a partially ordered set is such that every chain has a upper bound, then
Upper
this then this then this
set has
partially ordered set has a maximum
a
element. Okay, so axiom of choice implies Zorn's lemma. Okay, and using Zorn's lemma, you can prove one statement that somebody made, I forgot who has made, is a particular case of well-ordering theorem. Well-ordering theorem. It is something same as every subset of a natural number has least element. Okay. Actually, what it tells is, given any set, you can define an order on that set such that that order becomes a well order. Now, what is well order and so on? We will go too much of out of context, so I am not saying. But since I have told axiom of choice, I have to mention at least what is Zorn's lemma and well ordering theorem. So this is usual chain. First, axiom of choice. Using it, one can prove Zorn's lemma, and using Zorn's lemma, one can prove well-ordering theorem. See, it's a nice way of ordering hierarchy. First an axiom, then a lemma, and then a theorem. Okay. Lemma is again a theorem which is not of much importance as its own, but it is used to prove some other theorem. Yes, that's what lemma is. So anyway, but what is surprising is that you can go the other way around. That is, once you have Zorn's lemma, you can prove
Axiom of choice.
axiom of choice. Then you may ask, once you can prove something, why should you call it as axiom? It is a cycle, remember. You cannot prove Zorn's lemma without axiom of choice.
Axiom of choice.
Axiom of choice. So, if you take Zorn's lemma as an axiom, then you can prove axiom of choice. Or if you can take well-ordering theorem as an axiom, then using it, you can prove axiom of choice. So it is something like a cycle. If you believe axiom of choice, you can prove this. Otherwise, you take these two, one of these two as axiom, and then you can prove axiom of choice. In fact, they are all equivalent. Okay, the following are equivalent. That's the best statement. Not one implies the other. The following are equivalent. 1, 2, 3. Anyway, so for us, the axiom of choice, the way in which we have to use in our context is, given a collection of sets which are non-empty collection of non-empty sets, I can always form a new set by taking one representative from each of these sets. Okay. So having said that, let us go back to our theorem. What's the theorem that we want to prove? This one, theorem T2. There exists a subset E of R such that if I translate this set, I will get En, and this Ens will serve our purpose. What is our purpose? M star of union En is not equal to summation M star of En. Like that, I can construct my Ens using one E. So back to the proof of theorem T2. Proof of theorem T2. But before entering to the proof, please bear in mind that we are proving theorem T2 as a way to prove theorem T1, which says that you can always find a pair of disjoint sets A1 and A2 whose measure of the union does not coincide with measure of the individuals, sum of the measure of the individual. Now, without much delay, let us have the proof of theorem T2. So, as I told you, we are going to invoke axiom of choice. If you want to invoke axiom of choice, first I need collection of sets. And then from that, I will use axiom of choice and get a set. And that set is going to be the set E in the statement. There exists a subset E. This E I am going to construct with the help of axiom of choice. Okay. So for that, I need a family of sets. How do I do that? Consider a relation which I will denote like this on set C, closed bounded interval 0, 1, the unit interval. How do I define? By defining, take any two elements in 0, 1, x and y. I declare that x and y are related if and only if their difference is a rational number. That is, x minus y is a rational number. Hope the definition of the relation is clear. I declare two elements in 0, 1 as related, x related to y, if x minus y is rational, x and y are in 0, 1. I don't demand the difference should be a rational number in 0, 1. No, the difference should be a rational number. Then I will declare x and y are related. Do you see that this relation is an equivalence relation? Reflexive, symmetric, and transitive.
Yes, sir.
So I will put a dangerous word. Clearly, this is an equivalence relation. You should make yourself clear. Equivalence relation on set 0. Now, once you have an equivalence relation, you can talk about equivalence classes. For x in 0, 1, just to remind you the notation, square bracket x is the equivalence class of x. By definition, what it is?
Y belongs to
Set of,
0
set of all
such
y.
that x relates
Collection
to
of
y.
all y. Yeah, thank you. Y in 0, 1 such that
Which are related with x.
related to y. That means x minus y is in Q. Okay. For x element of 0, 1, square bracket x be the equivalence class of x, of the element x under the equivalence relation. Under the equivalence relation that we have defined, which I named as, or which I denoted like tilde. Okay. Now, what do you know about equivalence classes of different elements?
These are disjoint.
They make the partition of set.
Either they will be same or they will be disjoint, and their union will be the same as the set. That means they form a partition. Further, the set 0, 1 will be equal to union of all equivalence classes x in 0, 1. But I have to consider only those equivalence classes that are distinct. Okay. So now you have different sets. Do you have a collection of sets?
Yes, sir.
What are those collection of sets? They are different equivalent classes. Okay. So equivalence classes are non-empty, right?
Non-empty and
So you
disjoint.
have non-empty collection of non-empty sets. So I am in a situation to use axiom of choice, right? Let E be the set, to be precise, be the subset of 0, 1, consisting of one element from exactly one element from each of the distinct equivalence classes that contains exactly one element in each of the distinct sets in the collection equivalence class of X in 0, 1. You have different equivalence classes, no? And for the distinct equivalence classes, you form a set E by picking one element from each. Can you do this?
Yes.
Yes, sir.
That is by
Because they are non-empty.
axiom of choice.
Of
Okay.
choice.
In other words, so let me write once again a description of E. In other words, what does it mean? Picking one element exactly. In other words, for every X in 0, 1, the set E intersection equivalence class of X has exactly one element. You are forming a set by taking representative from each of the sets in the given collection. Such a set exists by the axiom of choice. Okay. So you got now one E, which is demanded in theorem. See the theorem T2. There exists a subset E of R. Now we have to see that this E has all the qualification mentioned in the theorem. That means with the E, I can form ENs by taking translations. Those ENs are disjoint and it satisfies these measure conditions. Okay. So now let us find the translates of E. E plus RL. Okay. If so, E part is clear, I suppose. Now I am going to translate E by rational numbers. If X and Y are in 0, 1 and X is related to Y, what does it mean? X minus Y is a rational number. Then X minus Y is in Q. Okay. Let R is equal to the difference, X minus Y. Then R is a rational number. But can you give a bound for this R, where this R will lie? X is in 0, 1, Y is in 0, 1. So where this R can lie?
-1 to 1.
It will be in the interval, closed bounded interval, -1, 1. Right? And R is rational. And you know that rational, set of all rational is countable. Okay. Let R1, R2, and so on be an enumeration of all rational numbers in -1, 1 intersection Q. You can enumerate because it is countable. Enumeration, I mean every rational number in -1, 1 is listed here and it is listed exactly once only. Okay. Now define En. Define En is equal to E plus Rn for n element of n. So you have got the second stage in the theorem. You got ENs. Now we have to verify that these ENs satisfy joint. Prove it. Suppose there exists a common element between En and Em. Suppose T is in En intersection Em. Okay. That implies T is in En and T is in Em. Now T is in En means T is equal to some element in E plus a rational number in -1, 1. T is equal to, let us say, E1 plus Rn. And that same T is equal to E2 plus Rm for E1 comma E2 in E and Rn comma Rm in Q intersection -1, 1. Do you follow? Is it okay?
Yes, sir.
Now, so T is in En, T is in Em will give this by definition. Now, do you see that? Therefore, E1 minus E2 is equal to Rm minus Rn.
Yes, sir. There is a rational and one is related to it.
So this is just we have translated to the other side. That's it. Now, please bear in mind how we constructed our V. We constructed our V such that not V, E. We constructed our E such that it has exactly one element from each of the
Class.
equivalence class. Okay. So I write our construction of E. You please give a thought and convince yourself. Our construction of E implies E1 is equal to E2. Okay. And that will imply Rm is equal to Rn. Okay. That means En and Em should be same. Okay. Because Rm and Rn, your enumeration means you are only putting distinct rational number. Therefore, Rm equal to Rn means M should be equal to N. Okay. Therefore, your En and Em are same. Okay. So this is how the proof will go. Of course, I don't wanted to spend more time on it. You can have a thought about it. So then En is a disjoint family. The hints I have given. If at all you feel some gap, you please think over and fill the gap. So thus En is a disjoint family. The second step is also over. Now E is contained in 0, 1 and Rn's are rational numbers in the interval -1, 1. Okay. So 0, 1 is contained in union En. Will you agree?
Yes.
Can you hear me? Do you agree with this fact?
Yes,
Remember, E is inside 0, 1 and Rn's are rational number between
Minus
-1 and 1, I suppose. Rn's are rational number between -1 and 1. Therefore, you can see that 0, 1 is contained in union n is equal to 1 to infinity n. Now, can you give me an upper bound for union en in terms of a set? This is contained in what? union n equal to 1 to infinity En is contained in which interval?
0 to 3.
0. Why it should be 0? Because Rns can be from -1 to 1.
-1 to 2, sorry.
-1 to 2. Right? Because E is in 0, 1 and Rns are in E is contained in 0, 1. This is the reason. And Rns are from -1, 1. Rns are rational from -1, 1. So you have this. So far, so good.
Yes, sir.
Now take measure.
Yes.
Therefore, so since M star is monotonic, M star of 0, 1 is less than or equal to M star of union En, n is equal to 1 to infinity, is less than or equal to M star of -1, 2. So we have used monotonicity of M star. Please keep in mind what are the properties of M star we used in this theorem. That will help for the next development. So we have used already monotonicity. Now, M star is not only monotonic, it is consistent with the length for the interval. Yes or no?
Yes,
Yes,
sir.
sir.
So what you will get is M star of 0, 1 would be
1.
1 less than or equal to M star of union n is equal to 1 to infinity En is less than or equal to 3. Do you agree?
Yes, sir.
Yes, sir.
Look at theorem T2. So you can find a subset E of R and its translation En such that 1 is less than or equal to M star of union En is less than or equal to 3. So that is main part. Now, in particular, M star of union En is not equal to summation n equal to 1 to infinity M star of En. That you should say. How does it follow? From the inequality, how this in particular thing follows. Can somebody tell me? Think over it is very easy. What is En? How do we define En?
E plus Rn.
Shift.
E plus Rn. So can you say something about it? Measure of En and measure of E?
Same.
They are
It
same
is same.
because M star is outer measure. I mean, outer measure is translation in way.
Translation.
So let me first note that. Note that. So this proves the main part. Now for particular part, I am doing like this. Note that M star of En, which is same as M star of E plus Rn, which is a translation, is equal to M star of E because M star is translation invariant. Okay. So now, what will be summation n equal to 1 to infinity M star of En? And this is true for all n. Okay.
Infinity.
Therefore, summation M star of En, n is equal to 1 to infinity. This is a series and each element in that series is a fixed number, M star E. So M star E, you are adding infinite number of times. So what will be this?
Non-finite.
Non-finite. Only in one case it can be finite, right? When M star E equal to 0,
0.
that case let us postpone. Assuming M star of E is not equal to 0, this cannot be finite. But what is M star of union En? What is M star of union En? It lies between
Greater than 1.
1 and 3.
One.
It lies between 1 and 3, whereas summation m star of En will be infinite, provided we are not taking m star of E equal to 0. Okay? Therefore, m star of En is equal to infinite. Okay, assuming m star of E not equal to 0. See, a series is convergent should imply nth term tending to 0. But here nth term is m star E. It is a fixed number. Okay, it will tend to 0 only if m star E equal to 0 for all. Okay, so we are not considering that case. We will see what happened to that case. And therefore, m star of union n equal to 1 to infinity En, which lies between 1 and 3, is not equal to summation n equal to 1 to infinity m star of En. Okay. Now, what if m star of E equal to 0? If m star of E is 0, then what happens to summation n equal to 1 to infinity m star of En?
0.
It will be
0.
0 because each one is 0. Okay. But what is m star of union En? It lies between 1 and 3. And so that case also, therefore, m star of union n equal to 1 to infinity En is not equal to summation n equal to 1 to infinity m star of En, even in this case. Even in this case. Is it clear? So the particular case follows just from this inequality. 1 less than or equal to m star of En less than or equal to 3. Are you okay with it?
Yes,
Yes.
sir.
So what did we prove? What did we prove? We proved existence of a countable family of disjoint sets such that m star of union is not equal to sum of m star of the individual. In other words, m star is not countably additive. We proved that m star is not countably additive. Okay, but we saw that due to countable subadditivity, countably additive and additive over two sets will be the same. Are you with me?
Yes.
Therefore, theorem T2 automatically proves theorem T1. Okay. So this ends the chain. This ends the chain. Okay. So here is a bad news. M star satisfies some nice properties, but M star does not qualify to be a perfect way of measuring sets. Why?
Not additive.
Because M star is not countably additive. In fact, it is not additive. Countable additive and additive are same in this context because M star is subadditive. Okay. So we saw that. So this is the conclusion. Thus, and that is a disappointing news. Thus, we saw that M star is not additive, or you can say not countably additive. Our aim was to define a measure that extends the notion of what? Extends the notion of length. So at this stage, we have a solid wall. You are not able to move further. You have a block. Okay. So how do we go about? But before answering that, one question that comes to our mind is this disappointing result, no, that M star is not countably additive. Can it be fixed by defining M star in a different way? Instead of working with the Lebesgue countermeasure, if we work with some other type of measure, can we fix this problem? That's the first question that comes to our mind. Is the question clear?
Yes,
Yeah.
sir.
We have a disappointing result, but this disappointing result or bad news may be perhaps due to the way in which we have defined M star. May not be proper. That may be the reason. So the question is, can we fix this issue by redefining or modifying our definition? Okay. So that question let us pose and try to answer it. Question. How should I write? Could this issue or disappointing news be fixed by using some other notion for measure? Some notion other than outer measure. Other than outer measure. For measuring. So instead of measuring using outer measure, can we measure using something else for measuring subsets of R? And towards this question, we have the following theorem. There does not exist a function mu with the following property. One, mu is a function on power set of R to 0 infinity. Mu is a function from the set of subsets of R into 0 infinity. 2, that is mu is from 2 power R to 0 infinity. Second property, mu of I is equal to L of I for every open interval I. I'm putting only open, but it will follow from all interval. Follow for all interval. And mu of union an is equal to summation n mu of an for every disjoint sequence an. And for mu of x plus a is equal to mu of a for all a subset of R and for x in R. Okay, before going to the proof, understand the theorem. I'm saying there does not exist a function mu with the following property. This mu is not M star, okay? M star does not satisfy all the 4 property we have already proved. Which property is not satisfied by M star out of these 4?
Third.
The third one is not satisfied by M star. Now I am saying there does not exist any mu satisfying all the 4 conditions. Okay. So once you prove this theorem, then the question is answered. You cannot fix this issue by just changing the definition. Whatever out measure you take instead of outer measure, whatever way you define, that definition will not give all the 4 properties. That's not possible. So Is that clear? The relevance of the theorem is clear or not? However hard you try, you cannot define a function mu satisfying these four properties simultaneously. Is that clear?
Yes, clear.
Yes, sir.
I will not, since we don't have time, I will not give the details of the proof in today's lecture. But what I will do is the following. The outline of the proof is as follows. Suppose there exists a mu satisfying all the four properties. Suppose there exists a mu, I am going by contradiction, satisfying all the four properties. Then what I will do is that using these four properties, I will prove that mu has, mu I don't know what is it, that mu has all the properties of outer measure m star I used in theorem T1 or theorem T2. Using these four properties, I will prove that if some function mu has the four properties, then mu will have properties of mu star I used to prove theorem T1 and theorem T2. What are those properties? Can you remember what are the properties we use? Monotonicity we used.
Yes,
Yes or no?
yes, sir.
Countable subadditivity we used.
Yes, sir.
Yes, sir.
Countable subadditivity for an arbitrary collection, whereas the third one is only for disjoint collection. Okay, please remember the difference. So I have used countable subadditivity and maybe translation invariant I have used.
Yeah.
So monotonicity I used, translation invariant I used, subadditivity I used. Suppose I can prove that my mu, if it satisfies this four condition, it should satisfy those also. That means mu should satisfy all the things that I used to prove theorem T1 and theorem T2. Then I can follow theorem T1 and T2. I can construct a sequence of sets such that mu of union an is not equal to summation mu of an. Yes or no?
Yes, sir.
That's what we did in theorem T2, right? In theorem T2, we got a countable sequence such that mu star of union an is not equal to summation and mu of an with by using some properties of mu, m star, not mu star, m star. So similarly, if I can prove that this mu satisfy the property that I have used in theorem T1 and T2, then similar to its proof, I can construct a countable family such that mu of union an is not equal to summation mu of an, and that will contradict third one. Yes or no? That will contradict the third one because third one says that mu of union an is equal to summation and mu. So my approach will be that if there exists a mu satisfying this four condition, mu will satisfy all the properties of outer measure that we used in theorem T1 and theorem T2. Therefore, following theorem T1 and theorem T2, I can construct a sequence of sets contradicting third property that I have listed here. And that's a contradiction. That means I cannot find a function mu satisfying all the four properties. Are you with me?
Yes, sir.
So this is how we will prove. So the details I will give in the next class. So what is the message from this? What is the message from this theorem? By trying to define outer measure in a different way, you will not succeed.
Yes.
You will not succeed. In other words, you cannot find a mu satisfying all these four requirements. So we have to give up something. We have to deliberately avoid one of these four conditions. Otherwise, we cannot construct a mu satisfying all the four conditions. You are with me?
Yeah.
So we have to give up one of these conditions, one of these requirement. So now you have to, think carefully which condition I should give up. Look at 2. I cannot give up 2 because I want something to have as an extension of length concept. Yes or no? And length concept I want to extend means if I take interval, my measure of the interval should be length of the interval. So there is no point in giving up second requirement. Do you agree?
Yes, sir.
Yes.
There is no point in trying to relax third condition because I want once I want a measure should satisfy this condition. You have already noted in our first few lectures. It comes from some fundamental principle like principle of exhaustion and so on. Therefore, third cannot be given up. Yes?
Yes. Yes, sir.
Now, suppose you want to define something as an extension of length. Length satisfies translation invariance. Okay.
Yes, sir.
And therefore, intuitively, we want measure also should satisfy the translation invariance in R. Okay. So any measure that extend the concept of length should satisfy fourth property also. So which condition we will give up?
The first one.
First condition, and we should not be too ambitious. We should not think for a measure that defined on the power set of R. We should be ready to relax, or I mean constrain the domain, restrict the domain. We should be ready to relax the requirement, first requirement, and we should be ready to work with some subsets of 2 power R, not the exact 2 power R. Are you with me?
Yes.
Yes, sir.
So the next natural question will be, how do we restrict? Which subsets I should take with, I should work with. Okay, 2 power R cannot be. Then which families of subsets I should work with? Of course, it should be some sigma. That is okay. That it should be some sigma algebra. Which sigma algebra I should work with? Okay, and that leads to the concept of measurable sets. So far we have defined only outer measure. And next we will define measurability. When will you call a subset as measurable? And that will lead to which sigma algebra that I should work with. So that one I will relax, and instead of mu from 2 power R to 0 to infinity, I will consider from a suitable collection of subsets to 0 infinity. Is it okay?
Yes.
Yes, sir.
So that's how we will be proceeding in the next lecture. Okay. First, we will prove this theorem. So there is no point in trying to define mu satisfying all the 4 conditions. We have to relax one condition, and the best condition to be relaxed is first one. Instead of working with 2 power R, we should work with some restricted class of sets. And what is the right restricted class of sets? That's the question. And that question leads to the concept of measurable sets. Okay. With that, let me stop. Thank you.
So,
Yes.
सर एक्चुअली पिछली क्लास में आपने बताया था कि एक ऐसी कम्युनिटी है जो एक्सियम ऑफ चॉइस को नहीं मानती है, तो वो
Yes.
फिर किस बिहाफ पे मतलब वर्क करते हैं? मतलब वो तो फिर ना मेजर थ्योरी पढ़ते होंगे, ना रियल एनालिसिस पढ़ते होंगे, ना कुछ और, मतलब कि ये सब कुछ तो उसी पे बेस्ड है ना, तो वो फिर क्या पढ़ते होंगे?
Now that's what I'm saying. It's only a minor community which doesn't accept axiom of choice, and they don't take axiom of choice, and for them these type of result will not be there. You have to accept it and go forward. That's it. But it is convenient to use it as an axiom so that many things will be as per intuition and many things what we want will work. That's why in majority, we want axiom of choice and we proceed. And whatever result you are using with axiom of choice, for those sets of mathematicians, definitely there will not be such results. Like every vector space has a basis. They don't have that result.
Then how can they read the linear algebra full course?
No, they have their own. That's why this is only minority. So if you want to read it more, I can give you a reference. It's really very abstract thing. I can give you a I can give you a reference. Let me just have a look into it, whether I have it in my notes. Otherwise, I can send you. Okay.
Okay, sir.
Where you can read more about this axiom of choice, why certain people disagree that it should be taken as an axiom, and for them, how to proceed with the other things and so on. If you want to read the history and more details, I can give you a good reference. But unfortunately, not now. Okay. I forgot to note it down. I can give you a website where they have collected the history and further developments of axiom of choice. Okay.
Yes, sir.
Yeah. But for us, and not only for us, for majority of mathematicians, it is better. The life is simple if we assume axiom of choice and proceed. Now, why to make our life complicated?
Yes.
And it is not something really unbelievable. Axiom of choice is intuitionally believable. Yes or no?
Yeah. Yes,
if I have a collection of non-empty set, I can always pick one from each and form a new set. So it is not something which contradicts our intuition. So if something is not contradicting our intuition, why not we take as an axiom and make our life simple? That is the way in majority of the mathematicians think. Okay, that's why based on that several things are developed, like in linear algebra or real analysis. This measure theory also, the construction of sets with such that the mu of union is not equal to summation is based on axiom of choice. If you don't give axiom of choice, you can say that mu star will be countably additive. Okay. But as I told you, just simple reason is that we want our life to be simple, and the axiom of choice, which is very well consistent with our intuition, makes our life simple. Then why unnecessarily to complicate? Okay. That's the only answer I can give. Thank you.
Thank you, sir. Have a good day.